So with rates, I also want to bring you to another thing that you should look out for when you see statistics in the wild. And this one is summarized by the idea of ignoring the denominator. In other words, ignoring the total amount of population in which you are comparing two different numbers. So I'm going to show you something, and then I want you to think about how this is possible. There were almost twice as many youth suicides in 2010 as there were in 1980. But the youth suicide rate stayed about the same from 1980 to 2010. How is this possible? Well, the answer is that the rate stayed the same, but the total number of youths changed. So in 2010, there were about twice as many young people as there were in 1980. So even though the youth suicide rate stayed about the same, there were more suicides simply because there were more young people. And so if you were to only think about that first statement, that there were twice as many suicides in 2010 as there were in 1980, you would think that there's been some massive rise in youth suicide, huge social problem. But what you'd be ignoring would be the fact that the suicide rate has been about the same. And obviously no amount of youth suicides is a good thing. It's a social problem regardless. But in terms of understanding the trend in it and what's actually happening, it's really, really important to be aware that the rate stayed the same, and it's really just the total number of people that have changed. And I'd say something else where you see this problem a lot is when people are comparing numbers of COVID cases across different countries or states. And I know, for example, when I talk to my grandparents, they're always telling me about, just the number of cases that are in their county or that are in, some state or somewhere. And one thing that almost always gets left out of the definition is what's the actual rate? And so comparing the number of cases in Florida to the number of cases in New Jersey to the number of cases in Nebraska doesn't tell you a whole lot, because you're missing out on the fact that the populations in all those states are different. So if you want to compare what's going on, it's really important to pay attention to your population number in which you are comparing something that's just a count. Okay, so the last topic for this lecture is going to be visualizing data. So we've talked about how to organize data in terms of numbers, using frequency distributions and somewhat related rates. The last thing I'm going to talk about here is how to organize data visually in the form of graphs and charts. And the first type of graph that we're going to talk about is a pie chart. A pie chart is a graph that is only appropriate for nominal level variables. So in other words, variables in which you can't put the different categories in any kind of order. And what you have with a pie chart is a circular graph with pieces that add up to 100%. So you guys have probably seen pie charts before. They show up in a lot of places. They're generally pretty intuitive to interpret. And on this slide, I have some goofy pie charts, and then I'll have some real ones on the next slide. So things that make the rockin' world go round, from the Queen song. My life broken into segments of sleeping, working, eating, and looking for things I just had a few minutes ago, which that second one is absolutely an accurate picture of my life. And pie I have eaten and pie I have not yet eaten. So in each of these, we have a circular chart with different pieces of the chart that add up to the total. And they show you, relative to the other things you're looking at, how common is one thing or another thing. Using the class data, I'm going to show you some pie charts for the questions where I asked you how much money it would take you to do different things. And here I'm just going to focus on whether you would be willing to do that thing for any amount of money, or whether you would not be willing to do that thing no matter how much somebody paid you. And with these, I'm drawing on questions that actually come from moral psychology and are often used to get at people's values and their sense of sort of what things are inappropriate to do and what things can be done with the amount of money it would take to do them, figuring into how wrong you think the thing is. So in this case, we're going to be looking at 4 different questions that you guys were asked in the survey. So how much money would it take for you to insult a stranger? broken down into whether you would insult a stranger for any amount of money or whether you wouldn't. And so the orange piece in this graph corresponds to people who would insult a complete stranger if given some amount of money. And the green piece of this graph corresponds to people who would not insult a stranger for any amount of money. Sorry, green-gray piece. And so what you can see here at a pretty quick glance is that 62% of the class would be willing to insult a complete stranger if paid some amount of money. 38% of the class say that no matter how much money you paid them, they would not insult a complete stranger to their face. Would you eat an entire chocolate cake in one sitting? 79% of the class said that they would be willing to do this for some amount of money. 21% of the class said that they would not be willing to do this for any amount of money. So you could pay them $50 million and they would not eat a chocolate cake in one sitting. And that one you can probably figure out where I would land. I would absolutely eat a chocolate cake in one sitting if you paid me some amount of money. This one is more interesting, and this is one where we have the number of people who would not burn the flag outnumbers the number of people who would do it. And so 55% of the class said that they would not burn an American flag for any amount of money, whereas 45% said that they would be willing to. And this tracks with morality research in general, where this is something that is sacred to a lot of people. And then this last one, would you spend a day at a nudist colony for some amount of money? 42% of the class said that they would not spend a day at a nudist colony for any amount of money, and 58% of the class said that they would spend a day at a nudist colony, if paid some amount of money. And in this question, I never actually specify if you have to join the nudist colony when you spend the day there, so I left it up to your imaginations, and I'm going to keep it that way. All right, so our next type of graph is a bar graph. And like a pie chart, a bar graph is also used for nominal level variables where the categories can't be put in any sort of order. Sometimes you can do a bar chart for an ordinal level variable, but typically you want it for nominal level variables only. And what bar graphs show is the number of observations in each category with vertical bars that correspond to the number of observations in each category. So in a bar graph, you have an x-axis, which is the horizontal axis, that shows the different values that your variable can take on, so the different attributes it has. And your y-axis shows the frequency or count, so the number of times that each of those attributes appears in the data. And in bar graphs, the bars don't touch each other. And this seems like a fine distinction, and in some ways it is, because we'll be talking about a graph where the bars do touch each other. But with a bar graph, the idea is that you're showing nominal level data. There is no order to the different categories that you're looking at, so they're separate from each other. They're just different things that you're comparing the frequencies of. So an example of a goofy bar chart, winners of Miss Universe have surprisingly all been from Earth. This is a bar chart that shows coolness on the axis, on the y-axis instead of frequency, but it makes me laugh. So you've got how cool the thing is, and then you've got these different things that are, a nominal level variable, because they're just different categories of things that you could lend to a friend. So cool to lend your car, cool to lend a hand, less cool to lend your handgun, your spouse, or your toothbrush, and then pretty cool to lend a T-Rex costume. So these are examples of bar charts. And now we're going to show some bar charts from the class. So what wouldn't you do for money? Here we have the exact same information that we did in the last slide in a different format. And what you can see here is that if you break it down by the frequency, or the total number of people who answered yes or no to each question in the form of, either saying that you wouldn't do the thing or giving some amount of money, we have 33 people in the class who would insult a stranger for some amount of money, and 20 people in the class who wouldn't. 42 people in the class who would eat an entire cake for some amount of money, 11 people who wouldn't. 29 people in the class who would not burn the flag, 24 who would for some amount of money. And then 31 people in the class who would spend a day at a nudist colony, and 22 who would not. So we're showing the same information that we had in that last slide with the pie charts, it's just a different format, where instead we're showing the frequencies on this vertical scale rather than showing the relative frequencies in the form of a circular graph. Right. The next kind of graph we're going to talk about is a histogram. And a histogram is a graph that's going to show up a couple more times in this class. The other ones will not as much. So if you weren't paying attention before, pay attention to this one. So a histogram is a graph that can be used for variables that are measured at the ordinal, interval, and ratio levels of measurement. So when you see that combination, it means you have a variable where the attributes can be put in order from least to most. So in all of these, you can put the attributes in order. And histograms show frequencies for consecutive values. This means that on the x-axis, or the horizontal axis of your graph, you have the different values of the variable in order from least to most. And on your y-axis, or your vertical axis, you have the frequency with which each of those variable values shows up. So a histogram is formatted in the exact same way as a bar chart. The only difference is that the bars touch. And again, I said kind of a fine distinction, but with a histogram, you're showing that they're consecutive to each other. So there's continuity between the different values that you have on your x-axis with the bars touching. So an example of a histogram is this one here, which shows the 20 most played Christmas songs, at least from 2000 to 2009, by decade of popular release. And what you can see is that we have decades on the x-axis, so our variable values here are the date of the song being released in order from least to most, or earliest to latest, and our bars are touching each other, showing that there's continuity as you move from the 1930s to the 1940s to the 1950s and so on. And you can see each bar corresponds to the number of Christmas songs released in that year, with the most Christmas songs you hear on the radio being released in the 1950s. And one other thing to note here is that, similar to a group frequency distribution, histograms can have values that are binned, so ranges of values, which is what you see here. So in that bar that's highlighted for the 1950s, you're seeing songs that are released between 1950 and 1959. So binned, similar to the group frequency distribution that we saw. Here's some histograms from the class data. The one on the left here is how certain are you that you'll get an A in this class? And so the x-axis shows the percent certainty that people reported, and then the frequency bars show you the number of people who reported that level of certainty. So what you can see is that most people were pretty certain that they would get an A in the class, with that high bar on the right side of the graph near 100. And as you move from right to left, which might be backwards on my camera, but as you move towards the other side of the graph, you have fewer and fewer people reporting that level of frequency. So relatively few people said that they were, 20% certain, or, in that range of values that they would get an A in the class. This one here shows the greatest number of drinks you've ever had. So you guys saw that in frequency distribution form already. You saw it as a regular frequency distribution, and you saw it as a group frequency distribution. And you get the same sort of information from this histogram, where you can see that most people in the class have, had relatively few drinks as their max, and then as you get to more and more drinks, there are fewer and fewer people who have maxed out at that amount. So these are just other examples of class data. And I'll also say that in all my years of teaching this class, I think the people who gave me 50 and 60 drinks or thereabouts, I think you guys might be my overall winners for this question so far. All right, so a last thing I want to talk about here with histograms is the shape of the distribution. And this is something else that's also going to pop up again throughout the class, at least for the next parts of this unit. And with distributions, we talk about distributions as having a skew or a shape. A distribution that is left skewed has most of the data on the right-hand side of the graph with a long tail sort of pointing out towards the left. So it's sometimes a little bit counterintuitive, but if it's left skewed, most of the data is on the right side, and you have fewer and fewer people moving out, or fewer and fewer observations moving out as you go towards the left. So it looks like it has a tail that sort of points out towards the left. If you have a right skewed graph, most of your data is on the left side of the graph with a tail that points out towards the right. So most of your observations are on the left side of the graph, and then you have fewer and fewer observations as you move out towards the right side of the graph. If you have a distribution that's symmetrical, like the one in the middle here, it's not really clearly skewed in one direction or the other, and most of your data is in the middle with, fewer observations as you move out towards both sides. So we'll come back to these next week, but for now, keep in mind left skew, right skew, and symmetrical describe the shapes of histograms, and left skew and right skew are a little bit counterintuitive because if you're left skewed, most of your data is on the right side and your tail points out towards the left. If you're right skewed, most of your data is on the left side and your tail points out towards the right. There's other types of distribution shapes that you might see as well. One that's worth a mention is one that is bimodal, and that means that you have multiple humps. So this is just an example pulled from the internet of a distribution you might see of test scores of people who did study versus didn't study, where they're clumped into these two humps. So you don't really have a dome-shaped symmetrical distribution, and you also don't have a distribution that's, has a hump and then a big tail going out in one direction. You just have two humps. So it's considered bimodal because you have two big lumps and no tails going out in either direction. All right, last order of business here for this lecture. And I will say this is, I think, the longest lecture that I have in this class, so if you've been watching this thing and you're like, oh god, when will this end? This is the longest one you're gonna have to sit through. So our last thing here are line graphs. And line graphs are useful for variables that are measured at the interval or ratio level of measurement, typically, so we're looking at numerical data. And line graphs are generally used to show a variable value over time. And your x-axis or your horizontal axis typically will show some sort of measurement of time passing, and your y-axis or your vertical axis will show the value of some variable. So for silly graphs, we have number of harpoons in space by year, where you have time measured in years on the x-axis and number of harpoons in space measured on the y-axis. Also, this graph, I don't know what the context is, but number of potatoes consumed over the course of a week, where you have time measured in days of the week on the x-axis and then kilos of potatoes measured on the y-axis. And I don't really have any good variables to show you a line graph with from the class data because I didn't measure anything over time. So instead, I'll just show you another example pulled from the internet, which is support for legalizing marijuana over time. So a lot of line graphs you see will be from polls like this where the same question is asked over and over again. And so what you can see here is that from the 1970s to more recent years, there has just been this pretty solid and consistent increase in support for legalizing marijuana in the United States. So we have time on the x-axis, and we have a variable value, which is percent of people who support legalizing marijuana, shown on the y-axis there. Right, so that's all I have in terms of content in this lecture, so I'll just leave you guys off with a couple of reminders. The first is that your second problem set is going to be due this Sunday, which is February 7th at 11:59 p.m. The optional review session or Q&A session is from 2:30 to 3:30 on Wednesday. So if you have any questions about the problem set or you want to go through an example, feel free to show up. If you can't make that time slot, feel free to also just email me to set up a different time to meet. And so that's all I've got for you here, and otherwise, if I don't see you on Wednesday, have a great week.